Hello, hello. For this video, we're going to do a proof of Theorem 1.7 because we've been a little loosey-goosey about talking about the pivot positions of a matrix, like what are the basic variables and the free variables. How do you know that you couldn't take one matrix and row reduce it in two different ways using two different sequences of Gaussian elimination operations and get two different reduced row echelon matrices that have pivots in different places in different columns? So I want to prove that that is not the case, that there's actually only one unique reduced row echelon matrix given any particular matrix. Now, one goal I have with this book is that I think linear algebra is a great place to learn about mathematical rigor because learning the reasoning for these facts is going to help you understand them and also help you learn how to figure out new facts because there's so many things to understand about linear algebra. There's so many theorems and so many different kinds of questions that are all sort of related to each other. So knowing how these things are related is a good way to understand linear algebra better. And because we're studying proofs in this reasoning, it's also a good place to learn about the idea of mathematical rigor, like the idea that every theorem has a proof. They're not just things that people noticed with a bunch of examples, but you can really come up with a proof beyond any doubt that all of these things are true. So I thought this would be a good one to prove because this fact is kind of not really proven in a lot of linear algebra books. People kind of glaze over this. So if you want to just like accept theorem 1.7 as fact, that's okay. You can skip the rest of this video. It's not really going to be important for anything later. But if you want to learn a little bit more about proofs, I think it's a cool proof. I found this proof, by the way, in a book by Kenneth Cutler. So I banged my head against this for a while and I couldn't figure it out. And I found a bunch of other books and his book had the best proof that I liked. So, first of all, a lemma is like a little mini theorem that you just use to prove a bigger theorem. So, this lemma is a fact that says suppose A and B are augmented matrices for two systems of homogeneous equations, with each matrix the same size and each in reduced row echelon form, and A not equal to B. So you have two different augmented matrices that are not equal, but they're the same size anyways. Then the two systems don't have the same solution sets. Now, this one seems intuitive. I don't actually want to prove it in the video, but just so you know, there is a proof. It's in the textbook. The proof is kind of technical and maybe a little tedious, but you can check it out if you want. Maybe I can just give you an example of what we're talking about here. So like if A is an augmented matrix, I don't know, 1, 2, 0, and there's a 1 here, and zeros over here. And B is similar to A, but not exactly the same. So something like that. So like they have pivot positions in different places. These linear systems have different solution sets. In other ways, you try to make them a little bit different from each other. There's going to be something that is a solution of one system, but not a solution of the other. So in this case, the only thing x1 can be in this one is 0, whereas in the other one, x1 can be anything depending on what x2 is. X1 is always just going to be negative 1/2 of whatever x2 is. So other way, like, or what if the coefficient parts are the same? Like so. So now they have the same pivot positions, but these parts are a little different. Then this difference between these means that like x2 and x3 are going to be different. So Yeah, that part seems pretty intuitive, but we're going to use that lemma to prove theorem 1.7. So here's how it will go. So we start by just saying, suppose that A is a matrix. Now, using the strategy in section 1.1 that tells you how to like row reduce something, you've done enough row reduction right now. I think you can believe that every matrix can be row reduced to reduced echelon form. So yeah, that strategy shows how every matrix is row equivalent to at least one reduced echelon matrix. But how do you know it's unique? Let's suppose that A is row equivalent to B and A is row equivalent to C, with B and C both matrices in row echelon form. We want to show that B must be equal to C based on that. Because if that's true, that means there's really only one matrix that is in reduced row echelon form that is row equivalent to A. What we're going to do is we're going to augment each of these with a column of zeros. And we're going to call this A plus is going to have A, but an extra column with all zeros in it. Same thing with B plus and C plus. Now, these are augmented matrices for homogeneous equations, like the lemma is talking about. And they're all row equivalent to each other, because whatever row operations you did reducing A to B are not going to change the column of zeros. And we know from theorem 1.1 that if two matrices are row equivalent to each other, then the systems of equations that they represent as augmented matrices have the same solution sets. And if they have the same solution sets, what does the lemma say about that? Well, it says if the matrices B and B plus and C plus are augmented matrices that aren't equal to each other, then they don't have the same solution sets. But we just showed that they do have the same solution sets. So we can say the augmented matrix B plus is the same as the augmented matrix C plus, and that means C must be equal to B. So that shows that if there are two reduced row echelon matrices that are each row equivalent to A, then it's really only one matrix. So that proves the theorem that the reduced row echelon matrix is unique. And from now on, we can talk about the pivot positions of a matrix. There's no way to get a different set of pivot positions doing a different set of row operations. Okay, cool.